Okay, good morning, everybody. I hope you had a very enjoyable evening yesterday at the banquet. My name is Pascal von Tobel. I'm at the Chinese University of Hong Kong. I'm here a TPC co-chair, and it is my great pleasure and honor to introduce today's plenary speaker, Sascha Barg. Just a few words about his biography. So he got his PhD in 1987 back in Russia at the famous Institute for Problems of Information Transmission. He then also spent some time there and then also in Eindhoven in the Netherlands. In 1997 he joined the Bell Labs where he stayed until 2002, and ever since he has been at the University of Maryland near Washington, D.C. I first got in touch with his work on expander codes. That's kind of how I got to know his work. But of course, he has also done many other things, like nice work on error exponents, then work on codes for fingerprinting. And most recently, he work that got a lot of attention. In particular, he got the Best Paper Award of the Information Theory Society last year. This is his work on locally recoverable codes. He also worked a lot of codes on various metrics, not just Hamming metric, and I think part of his talk today will be on these things. So with that, I don't want to take any more minutes from him, so please welcome Sascha Barg.
Thanks very much. Can we have this working? Oh, yes, thank you. Very good. Thanks for the invitation to speak here. It's a great honor, and I'm humbled to follow in the footsteps of the great scholars who spoke here before me during this week. And thanks also for the kind introduction and for the award to the Society for the award for this locally recoverable codes for storage. It would be a natural thing to speak of the codes for storage in this talk, but we covered them in detail together with Itzhak Tamo in a tutorial this past Sunday in the span of a few hours, and so that I don't repeat myself. For this talk, I chose another topic on codes in various metric spaces and metrics in general. And so this topic is not very familiar to maybe some coding theorists in the audience. And my goal here is to popularize it somewhat, because if more people know about these kind of problems, then I'm sure that new applications and links arise. And if this happens in a year or two, then I think that I will have accomplished my goal. So we speak about coding theory in a class of metric spaces, and the range of problems that I'm considering is related to distance distribution of codes, weight distributions, to duality of linear codes, to a particular class of metrics related to partial orders on the coordinates. I will briefly mention matroid invariants without devoting that much time to them. I will speak of simple channel models matched to these ordered metrics, and there will be an application to polar codes. I will mention again briefly combinatorial context in which these metrics naturally live, and also some further extensions. The problems that I'm considering are motivated by applications, and I will in fact devote perhaps 20 minutes of this talk to describing a description of various motivations of these metrics and these problems. But then at a certain point, the logic of research takes us beyond applications, and the answers that we seek maybe don't directly go back to those applications. But I guess that's acceptable within this type of research. And some parts may become rather technical, but I tried to keep technical details to a minimum. And I also developed this talk as a sequence of somewhat independent parts. And so even if one part looks too technical, it will end quickly and something else will begin. It is possible to rejoin. This has been my part-time hobby for the last 10 years or so, and this talk draws on works with a number of collaborators, some of them my students, some have graduated, so the students' names are underlined there, and also with Marcelo Führer, Maxim Skryganov, and others, maybe to a lesser extent. Over the years, this work has been supported by NSF, in particular through this project on ordered metrics and their applications, and some other projects during the years, and I'm grateful for this support. Here is the outline. I will start with a very classical introduction, more or less textbook material. This is part one. Then go to motivate the class of distances on strings over a finite field that I'm considering, and devote, as I said, some time to motivations, and then move to results about linear ordered codes. Speaking of weight distributions, or more appropriately, as we shall see, shape distributions, I will speak what it means to be a dual code. This question actually turns out to be rather non-trivial. Then move to channel models, and channel models will connect with polar codes in a particular situation of non-binary input alphabets. And well, there will be some other applications, some other extensions. Starting at the beginning, a linear code, well, this is what we teach in our classes, is a linear subspace of a space of n-dimensional strings over a finite field. It comes equipped with a generator matrix, parity check matrix, and it comes also with the weight distribution. Weight distribution is nothing but a set of n+1 numbers, where bi is the number of code words of Hamming weight I in the space. So we are, for the moment, we are considering Hamming weights. This is very, very standard. Weight distributions have two particular kinds of applications. One is studying structural properties of codes, perhaps equivalence, existence versus non-existence. And also they are useful in computing the estimates of the error probability of either complete decoding, map decoding, or various incomplete versions of decoding, such as perhaps even undetected error. So this is a classical application. Now, the dual code, denoted here C-dual, is a linear subspace of the same space. It is formed of vectors y, such that for every code vector in our code C, the dot product xy is 0. That's a linear space, of course, and it is entitled to its own weight distribution, which is denoted B-dual here. That's again a set of numbers which refers to the number of vectors of Hamming weight I in the dual code. We can write those weight distributions in a polynomial form, use generating functions of those numbers. These are called weight enumerators for the code, for the dual code. Here, x and y are nothing but formal variables that are introduced here for the ease of manipulation with these numbers. And if we do that, write those polynomials, so without really changing anything structurally, we'll write this in a polynomial form. Then these two polynomials come, they are related through the famous McWilliams theorem, again a classical topic in our coding classes. It says that to go from the dual weight enumerator, BC dual, to the weight enumerator of the code, we need to perform a simple linear transformation of x and y, shown here, and then we can move between the weight distributions of the code and of the dual. This is indeed one of the basic facts of coding theory, and it is useful for classification of codes, estimates of error probability. Famously, there is a well-developed application of this theorem to deriving bounds on the size of the code. So given the minimum distance, what is the largest possible size of the code, of the packing, of the space? What is the maximum number of messages that we can transmit with a given distance between the code words? And extensions of this theorem, this is actually a vibrant research area. They are used in many contexts, including sphere packing optimality of lattices. And very recently, there was a breakthrough result where they proved optimality of the lattice E8 and the Leech lattice in their respective spaces. R8 and R24, and this happened only this past March, using the development of the McWilliams theorem. So this continues to bear fruit, and it develops in a number of directions. Now, there are two approaches to proving this theorem, both from the original paper by Jesse McWilliams. One is using Fourier analysis, and the upshot of that calculation is that if we take this equation and solve it for an individual coefficient on the right, maybe we want to know what is the number of code words of weight j in the dual code, that's a linear combination of the weights in the code. The coefficients in the linear combination are evaluations of some discrete orthogonal polynomials of one variable. And in the combinatorial context, these polynomials, the Krautchuk polynomials, or rather their values, they form eigenvalues of certain matrices naturally associated with the Hamming space. This notion of eigenvalues will show up only once more toward the end of the talk, but let me point out that that's a useful combinatorial point of view at this picture. There is also a linear algebraic approach to this theorem, so I'm switching the point of view. And to develop this approach, we look at the ranks of the submatrices of the generator matrix here. Start with a subset of coordinates and look at the rank of the submatrix whose columns are indexed by the elements of A, and call rho of A the rank of that submatrix. Let K be the dimension of the code, and introduce a Whitney function of the code. It's a polynomial of two variables written here, and there are reasons to do that, but perhaps it would be too much to explain it now. But interestingly, if we write this function for the code and for the dual, then going between the two codes is as simple as it gets. So to go from a Whitney function of the dual code to the primal, we simply need to swap the roles of x and y. It cannot be any simpler than that. And this is indeed a McWilliams type relation made explicit by Green's theorem, which says that the weight distribution can be computed from the rank generating function by the relation shown here. So we can take z and obtain the weight distribution of the code. This connection indeed extends to the invariants called higher weight enumerators or support weight enumerators. They were first introduced from the setting of the wiretap channel, combinatorial wiretap channel, Ozar-Weiner's wiretap channel type 2, isolated by Victor Y. And I made this little remark about this type of relations for higher weights a good 20 years ago. So this can be taken a bit further. And indeed, if we consider a code as a representation of a matroid on this finite set of n elements, then ZC is well known it is a Whitney function of the matroid M. I will not use this in the rest of the talk, perhaps mention just once more. The last concept that I need to mention in this introduction is that of an orthogonal array. Again, this is not heavily used, but it will show up once in an interesting context. So what is an orthogonal array? This is something that appeared in statistics in the 1940s in the works of Rao and his collaborators. And what it does, it approximates a uniform distribution on the set of strings. And by which we mean the following. Consider these 8 vectors of dimension 4, binary vectors. If we take any 3 columns and look at the rows in these 3 columns, then each possible row appears the same number of times. Here exactly once. It can be twice, it can be 3 times. And in any event, this is called an orthogonal array of strength T. So as we see, it approximates the uniform distribution in the sense that if we isolate any subset of T coordinates, then the distribution of those substrings is uniform. Orthogonal arrays also appear in the combinatoric context of algebraic combinatorics as an example of designs in the association schemes, although this will not be needed for the rest of the talk. So orthogonal arrays. Now, from here, let us discuss various distances. Now walk away from the Hamming distance and related concepts. There is a variety of distance-like functions, and their number has been growing as new applications arise. the standard concepts here are the Hamming distance, the Lie distance, Levenshtein's distance has been popular in the last couple of decades because of applications by bioinformatics. Distances on strings, such as and permutations, such as the L1 distance, the Kendall tau, was used in rank modulation for flash memories, the L infinity distance on permutations, subspace distance with its applications in network coding, rank metric, of course, and ordered metrics. So this is something that interests me in this talk. They were introduced by Niederreiter from a perspective of approximation theory, and independently by Rosenbloom and Tsfasman a few years later from the perspective of Reed-Solomon codes. There are many more distances, and if you are really interested, you can go to this book and you will see hundreds, if not thousands, of other possible metrics on strings. It's indeed a very useful list with references. So moving to ordered distances. Before defining them, I want to motivate them. And there are at least 5 or 6 different motivations, of which I will mention 3. An application from wireless, multiplicity codes, and approximation theory, and there are 2 more. Now, moving to wireless, this arose in one paper by Taveldar and Vishwanath 10 years ago, where they considered a slow fading point-to-point MIMO channel, given by this familiar equation. The M is the time unit, and in one particular version of that system, they considered a set of parallel fading channels, where the equations for the received signals are shown here on top. There are parallel links, and they were interested in designing universally optimal sets of signals that work for every combination of those links that are not in outage. And in one further specification, they looked at the system with the following ordering. If link J is in outage, then so are links 1 through J minus 1. So there is this ordering on the links. And what matters here is the index of the last unreliable link, or the first reliable link, if you will. And from here, in fact, Ashwin Ganesan and Pascal von Tobel picked up this context and constructed what they called universally decodable matrices that work for arbitrary configurations of such arbitrary numbers of links not in outage, well, given certain restrictions, of course. So that is one approach. The metrics have not, we have not shown any metrics for the moment, but what is important is this ordering of symbols within one transmission, within the R transmitted signals within one time slot. Switching the topic, not the topic, but going to a point of view of Reed-Solomon codes. This is the same metric, but approached from another perspective. A Reed-Solomon code, again, very well familiar. We start, so here is how one way of constructing them. We take n elements, n points in the finite field. We take a linear space of polynomials of degree up to k minus 1. Evaluate one polynomial at the endpoints. That gives us one vector of dimension n over the field. And if we evaluate all such polynomials, we get a linear subspace. And what is interesting here is that a polynomial, of course, degree k minus 1 has at most k minus 1 zeros, so the other n minus k minus 1 evaluations are non-zero, and so that is the minimum distance, the minimum weight, Hamming weight, of a non-zero vector in the code. Rosenbloom and Tsfasman asked, what if we evaluate not the polynomials, but also derivatives of those polynomials, so we get a code of length 2n now, or maybe 3, or generally r derivatives. Let us stick to 3 evaluations, so the polynomial itself, the first and the second derivative. And again, we want to count the number of non-zero entries in the vector. But what matters now is the multiplicity of 0 at the point a1, so that if if the evaluation and the derivative are 0, then a1 contributes 2 to the count of zeros. And now we see that if we add up those zeros with multiplicities, then they cannot exceed the degree of the polynomial. So what matters here is the location of the rightmost non-zero entry in each block. Let's say if this is non-zero, then we know that the multiplicity of 0 is 2. That is how this metric arises in another context, and recently this approach was extended to multivariate polynomial in the context of locally decodable codes in the computer science community. With that, let us define the distance. As we said, we have n blocks, and each of the blocks has length r, so I write these blocks in a matrix. One row corresponds to a little block here on the previous slide, and what matters, as we said, is the location of the rightmost non-zero entry. So we add those locations and call that the weight of the vector. So we add 2, 3, 2, 0, 0, 4, and hopefully get 11. And so 11 is the weight of the vector. This. From here, we can move to a formal definition. We start with vectors of dimension r, and we call the weight of the vector the location of the rightmost non-zero entry. And then we extend it additively to n consecutive blocks of r elements over some alphabet, mostly a field for me. So the total dimension of the vector is capital N, which is little n times r. So we have n rows, and the length of each row is r. In each row, we write down the location of the rightmost non-zero entry, add them, call this the norm. Is this indeed a norm? Yes, well, it's a little exercise, but you can convince yourself that that's a proper weight, and it defines the proper metric on the set of vectors. And as I said, it was considered by Niederreiter and Rosenbloom-Tsfasman independently, and so I call it the NRT metric, and well, some other people do the same. But the term ordered metrics is also an accepted usage. So why did Niederreiter come up with this definition? And now we speak of approximation theory. So this is still along the lines of motivation of the norm. It's quite unexpected that this distance on the strings over a finite field can arise in the context of computing multivariate integrals. And it does so as follows. What we want is to evaluate a multidimensional integral of a well-behaved function. We need bounded variation or condition of a similar kind on the unit cube in the real space. This is difficult, and it is much easier to compute an average value of the function over some finite set of points. And what we hope is that this is an approximate equality. And the question becomes when we can estimate the error of this calculation. This is controlled by what is called discrepancy of this finite set of points. The discrepancy can be defined as follows. We take some class of subsets of the cube, and jumping ahead, those subsets will be rectangles of this form. So we take all the rectangles with parallel to the axis and compute the following difference. So what we want of a uniformly distributed finite set of points is that within a subset, the proportion of the points is roughly the volume of the subset. Then it is uniformly distributed. We take the worst possible difference, so max or supremum over all R in this class of subsets, call this discrepancy. And it turns out that this discrepancy indeed controls the error of approximation. And so this started in the works of Hermann Weyl exactly 100 years ago. And van der Corput was the first to systematically construct uniformly distributed point sets in a cube. And what is interesting here, you can see that a set of points with small discrepancy is very, very different from a random subset. It's entirely non-random. It has a lot of structure. So this is not something one would expect before working on this problem. What kind of structure might one need? So what we want, as we said, we take the set of axis parallel rectangles, and we look at the number of points in this set from my collection of points over which I evaluate the integral. And what is desired here in one approach is that every rectangle of a fixed volume contains the same number of points of my configuration. So in this case, people call it TMS nets. That was Niederreiter's notion that he introduced in the end of the 80s. And there is a precise definition of the net, which doesn't matter. It just fixes the parameters. But again, we want that the intersection of my set of points with every box of this kind is fixed. equal to q to some power t, doesn't matter what t is, and here's the punchline. There exists a uniformly distributed set of points with these properties, if and only if there exists an orthogonal array of that particular strength with respect to the ordered metric. It's quite amazing, but this happens. So we need orthogonal arrays with respect to the ordered distance, and before we even realized that, we introduced the notion of the distance. That's what Niederreiter did, and then this theorem was established by Lawrence and Malin-Schmidt in 2 independent papers. I will not say anything else about approximation theory, so perhaps this is enough of a motivation from this side. Oh yes, there is also a detailed account of this, and in fact more general, by Maxim Skryganov. Coding theory and uniform distributions speaks about MDS codes with respect to the ordered distance and uniformly distributed sets of points and their discrepancies. Very well. There are 2 other motivations. If you are familiar with for instance, the Guruswamy-Sudan list decoding algorithm over its Solomon codes, which fits polynomials with multiplicities, then you realize that this must be related to this metric, and that was made explicit in the work of Rasmus Nielsen in '99, and there were later extensions to multiplicity codes, maybe not exactly connected to what I'm discussing, but still close, in particular by Guruswamy-Wong. And there is also a work by Jim Massey and Shirley Sarkonek on linear complexity of sequences, wherein, again, they needed the same distance on strings. So even though the definition seems not so natural, it can be approached from at least 5 different sides. So perhaps that's enough of a motivation to consider it. Having finally introduced this ordered distance, what is it that one might want to accomplish here? Well, let us try to construct a little theory of those ordered codes. We have a code in the space over a finite field of length capital N, which is little n times r. Let's say a linear code. And we want to discuss the basic concepts, and as you will see, some unexpected issues arise. For instance, what is the proper definition of the weight distribution of the code? This is not immediate, as I'm hoping to convince you a bit later. This was started by Bill Martin and Doug Stinson in '99, and then Punabasu, Pukayasta, and Dyke worked on that a few years ago, and we continued with Marcelo discussing and perhaps establishing what is the right way to look at these codes. Duality of codes is again a non-trivial question. We will see that what comes to mind with respect to defining a dual code is in fact not correct, and one needs to make adjustments to the point of view to be able to properly work with these linear codes with respect to this ordered distance. Now, if we have a metric, it would be good to have a channel for this metric, for which this metric is sufficient statistic for map decoding. And it is possible to define such channels. This is not very difficult and maybe not even very interesting. But what is nice is that these channels come up in a particular setting for polar codes, which I will show also in a few minutes. Combinatorics of the ordered space is again non-trivial, and it helps one to study bounds on the size of codes in terms of the minimum distance. That is something we did with Punabasu. And then linear codes in general, linked to matroids, and extensions to wiretap channels with this ordering is also possible. And this is something we looked at with Woo-Myung Park, and it took us about 5 or 6 years to write a paper, but now it's finally published. Infinite orders, well, there will be only a very brief mention. What happens if we allow this chain R to become infinite? Something very interesting happens even combinatorially, and this will be my last page because it would not be possible to devote more time to it. It becomes very technical rather quickly. So this is an approach to a theory of such codes. Let us look at what happens with the weight distribution. We have 2 linear codes, C and C dual, and we define the weight as was explained before. And given a linear code and the weight of every vector, we can define the minimum distance, the minimum weight of a non-zero vector. The NRT distance, if you will, One can study bounds on codes in terms of the minimum distance. That's a well-recognized question, but there is a problem if you look at this definition. Namely, a McWilliams type theorem does not hold. What does this mean? Well, it means that the dual weight distribution is not uniquely determined by the weight distribution of the code. So there is a problem with this definition. Something is going on. And what does it take to be a good weight distribution? What is a correct definition? As I said, there are two approaches, right? It is a figure of merit for map decoding on some channel, hopefully naturally defined channel, and it supports some kind of McWilliams theorem. All right. So what is the answer? It comes from a combinatorial perspective. The correct, quote-unquote, invariant is not the weight itself, but it is the shape of the vector. Rather than summing these numbers, we use all of them as a string of 5 digits here, from 0 to 4. There are 2 blocks of weight 0, 0 of weight 1. There are 2 blocks of weight 2, 1 of weight 3, 1 of weight 4, and call this the shape, a shape. What are the reasons for this to be a good invariant? Well, combinatorially, the reason is as follows. It turns out that what we need is that the isometry group of the space acts transitively on shape spheres. And moreover, not only it does so, but this is the coarsest possible invariant of this kind. If we lump them further together, the shapes make something coarser out of them, then the transitivity will be lost. So once you see that type of invariant, then you realize this is what you should take, and this is where you should push for a McWilliams type relation, and this is what will describe your code combinatorially. And in other words, one might say that a set of pairs forms what is called a translation association scheme, in which classes are indexed by the shapes. So this simply refers to a description of those codes in the context of algebraic combinatorics. And then there are natural channel models for which shapes form sufficient statistics. Well, maybe these reasons are enough. And well, a brief remark is that the isometry group of the NRT space was found in 2003 by Lee. And what we can do what type of transformations can we use? Well, we can multiply every little block by a triangular matrix with a non-zero diagonal. This does not change the location of the rightmost non-zero entry. And we can permute those blocks at will. So this amounts to a product of a group of upper triangular matrices, semi-direct product with a symmetric group. And one can check that it indeed acts transitively on shape spheres. Rather than looking at the automorphism group, we realize it is possible to establish a McWilliams type relation. So this was done by Martin and Stinson and Skriganov. And now we take, in fact, the relation goes with respect to those shape invariants. And there is a linear transformation that takes us between the code and the dual. This has been done. And this is where we picked up with Punabasu. So we asked ourselves, if there is this type of relation, is it possible to derive what they call linear programming bounds on the size of the code? To do so, one has to solve this with respect to an individual coefficient. This is the relation. And what we realized, what arises here, is a sequence of orthogonal polynomials now of R variables. Orthogonalities with respect to a multinomial distribution, so they might be viewed as multivariate extensions of Krautchuk polynomials or eigenvalues of the ordered Hamming scheme. Again, thinking combinatorially. Now, linear programming bounds in the classical context, if you have seen this derivation, they rely on the location of zeros of univariate polynomials. But here we have multivariate polynomials, and nobody knows anything about their zeros. They are extremely difficult to control. And so it takes a different set of technical tricks to derive these bounds. So this is what we did. It gets rather complicated computationally, but we were able to derive bounds, and I'm showing this plot. I wish I could do it better, but I lost the numbers in the span of these years, and so I could only copy this from some files. But in any event, there is a decent picture that arises with respect to the asymptotic bounds. So this is the rate, this is the minimum relative distance, There is a Gilbert-Washamov bound, which was derived by Rosenbloom-Tsfasman, and there are upper bounds that one computes from the description that I presented. So this question is kind of resolved in the same way as it is resolved in the classical context. It is also possible to take a linear algebraic perspective. As I said, in the classical context, one might think of this in terms of matroids and their invariants, but now we have some orders. Thinking of ordered matroids, is it possible to define one? Well, in a nutshell, this is difficult. There are multiple definitions, and none of them properly works in general context. But in the NRT case, it is relatively simple. We can define, we can look at the ranks of submatrices of the generator matrix, but submatrices have to respect the order of the coordinates. One can define a multivariate rank nullity function, and this is interesting because previously this type of relations was not, they didn't have it in combinatorics, but it is possible to define those multivariate rank nullity functions, Whitney functions, and going between the code and the dual amounts to a permutation of these variables. So that was quite pleasing that it was possible to establish that. This is something that we did with Wumyong. And the motivation comes for me from two works by Alain Sokal, a very nice survey on a multivariate Tat polynomial, which explains that working with multivariate invariants, in fact, is on the one hand easier and on the other hand more powerful. It enables us to prove more general results. And there is an old work with Alexei Shichmin on binomial moments that was another motivation for me to look in this direction. So linear algebraically, it is also possible to look at these codes. Again, switching the topic, what does it mean to be a dual code with respect to the ordered distance? Well, looking at this picture, one realizes that while the distances in the code, as we said, are measured from the left, the location of the rightmost non-zero coordinate, in the dual code we must measure them from the right. Why? Well, because otherwise it doesn't work. That is not enough of an explanation. Why do we have to do that? That question is in fact non-trivial. And so I want to stress the takeaway from this part, from this slide, is the following. Yes, why the distance is measured differently? The answer can be phrased as follows. We define the dual code by the dot product, but it turns out that this dot product does not automatically respect the combinatorial structure of the code. And in fact, generally, a code and its dual live in different metric spaces, and those metric spaces in general are not isomorphic. Here they are, but thinking more generally, they may be not. So one has to take great care in these more complicated situations. In the Hamming space, there is this canonical isomorphism which lumps everything together and there is no difference. But in this case and other similar cases, and this is indeed an important point, if you have a complicated metric and you want a dual code, you need to be very careful about the notion of duality. This question was addressed, and in fact, we made some progress in the work with Marcelo and to his students. I will show the names on the next page. And we addressed it in a slightly more general context. Rather than looking at one particular partial order given by this NRT approach, NRT definition, let us look at an arbitrary partial order on the set of coordinates. So let us say there is a finite set. There is a partial order on the strings over that finite set. And an ideal in that partial order is nothing but a downward closed subset. So if a point is in the subset, then everything that is below that point in the order is also in the subset. Those are called ideals in the theory of partially ordered sets. Brualdi and co-authors defined a poset weight of a vector as the smallest size of the smallest ideal that covers the non-zero coordinates of the vector. Now, of course, if one wants dual codes, one thinks of the dual posets. So what's a dual poset? Consider two partial orders. This element is less than, sorry, going back, this is less than this one, and this is less than this and that. Or here is another partial order, this is less than these 2 points. What is the dual order? The dual order, we flip the signs. So now what is below is greater than what is above. And a poset is called self-dual, of course, if it is isomorphic to its dual. For instance, this poset is self-dual, A is less than C, B is less than C and D. And then we flip the signs, and we can relabel the letters so that this partial order is the same as this. So this is self-duality. And a theorem that we proved with Marcelo and his students, Luciano Felix and Marcos Preafico, was that, informally speaking, the dual codes agrees with the dual partial order if and only if that order is self-dual. Now, I'm not defining what it means to agree. This would be technical, and indeed this answer is expected, right? If you ask yourself, what do we need? Well, probably the partial order needs to be self-dual, but it takes you a little while to understand this and to convince yourself that this is a correct approach. But in any event, for partial orders, this question of duality in a certain sense is resolved in this recent work. So that was a rather pleasing development. Let us switch to channel models. So we have this obscure NRT metric. Is there a decent communication channel that is kind of connected to it? Well, here is one possibility. Let us consider what we called, with Wumyong, we called it an ordered erasure channel, for the lack of better name. It has 4 input letters, a pair of bits, and it either transmits correctly or it erases. But it erases according to the order. So it either transmits correctly or it erases the first bit or both bits. But it never happens that it erases the second and does not erase the first. All right? So there are 4 inputs, 7 outputs. And that's a memoryless symmetric channel with additive noise. Capacity is an exercise, and it wouldn't be that interesting to do that. We did it nevertheless. And we can define an analog of the Curie symmetric channel, again, carrying this order of errors. Now, it takes a little while to absorb this, but indeed what we wanted is to account for the order of the bits in the transmission. And interestingly, one can convince oneself that the probability of error events is monotone according to a certain ordering of the shapes of the error vectors. So it is possible to design those channels. And it is possible to even take it further to ordered wiretap channels if desired, where the adversary can access parallel links between the legal transmitters, the receiver and the sender and the receiver. But accessing links up the line with increasing numbers is progressively costlier for the adversary. So there is this natural ordering on the eavesdropping. And it is possible to push an analog of the Weiner's and other Weiner's approach into this context, compute again secrecy capacity. But it doesn't take much of an insight to do that. Nevertheless, we did it with Wumyong. But what is interesting about this definition is that it suddenly arises for polar codes over an alphabet of 2 to the R letters. Not binary, but 2 to the R, where R is the same R as before. This is the length of the little block. So let us say we have data. U1 is a letter with R bits, so is U2. And we perform the Arican transform to obtain 2 channel bits by multiplying by this matrix. And what is the operation? Addition modulo 2 to the R. So we add them and do this modulo 2 to the R. It turns out that if you develop Arican's approach in this context, then the picture converges, the virtual channel converges, but they don't converge to 2 levels. Rather, they converge to R+1 levels, generally. So there are symbols that carry 0 bits, that carry 1 bit, carry 2 bits reliably, carry 3 bits. And the total number of bits reliably transmitted, again, equals the symmetric capacity of the channel. So this example, in fact, is for this ordered erasure channel. And as you see, these channels are indeed very useful as a testing ground of this multi-level polarization. This is proved using, well, there is more than one way to do this. But if you use the Bhattacharya numbers for the non-binary, but it is possible to define them in this way, then there arise R+1 extremal configurations. And there is a certain monotonicity of the subchannels. Namely, the extremal configurations are only on this form for every j. So either all these are 0 or just one is 1, so then the bit is unreliable, on the right are reliable, or 2 or 3, but there is this ordering, so they are consecutive. The ones are consecutive in this picture. That is interesting, and an analysis of this can be performed using this ordered metric that I discussed. So it proved useful, at least in this context. It provides an approach to obtaining this new result about polar codes, and we did this with Wum-Yong, and this was published a few years ago. And as I said, and I will repeat, there are other approaches to this multi-level polarization, in particular a nice work by Sahebi and Pradhan, which was published contemporaneously. And the question of the number of those levels to which the symbols polarize is to a large extent unresolved, as far as I understand. I'm not able to say, given the channel, whether there will be 2 or more extremal configurations. In general, they may be up to r+1, but will all of them be realized? What is the probability mass function? Namely, what is the proportion of channels that will fall on this step of this ladder? I don't know. And it seems to be a difficult question, at least I mean, for me. I don't know how to approach it. So this multi-level polarization, maybe it's not particularly important in applications, but it is kind of annoying that it is not possible to understand it in a good way, what happens with it. Very well. This is my last slide before some concluding remarks. And this last slide speaks about one other topic, one other work that we developed jointly with Maxim Skriganov. This goes about the following question. So let us say, I would rather put this to be R. So we had R symbols ordered in one block, but let us say we allow this block to be infinite. So there is just one block of length R, but R is infinity. And we don't repeat them, because why would we repeat an infinite block? It's already infinite. And so we have those symbols over, let's say, Zp. P is a prime number. And we add them coordinate-wise modulo P. And they naturally form a group, call it X. And this group is formed as a tower, or the decreasing infinite tower of subgroups. And what is X2? This is a set of strings that have 2 zeros in the beginning, and so on. So Xm is m zeros in the beginning. The intersection of all of those groups is empty, and we define the metric in the same way as we defined before. So this is the maximum location of this is the location of the first non-zero entry. Right? So everything before j is 0. This is a well-defined metric. It is well known, in fact, in many problems in number theory. Let us not go in that direction. But it is possible. So in the beginning, I spoke of adjacency matrices of the Hamming space and Kravchuk polynomials arising as their eigenvalues. It is possible to define adjacency operators here. Why would one do that? Well, because we want to develop a combinatorial understanding of these infinite strings. It is hard to say why, though. But there is something interesting that arises once you do that, once you push this theory. So it is possible to define natural adjacency operators. And it is possible to compute eigenvalues of those operators. And it turns out that what arises instead of orthogonal polynomials is a set of functions on the space of square integrable functions on this group, which have the properties of a multi-resolution approximation. So in fact, this gives rise to a large class of wavelet-like functions. So if you are familiar with standard constructions of wavelets, they require what is called self-similarity, that there is a natural dilation operator that takes what they call a mother wavelet and constructs the wavelet basis by dilating the supports. Now, here self-similarity is absent, Well, that is not a problem. This is called second generation wavelets in the literature, so it's okay to consider these functions. And what is interesting is that these functions are not only wavelets on this type of structures, those had been considered before, beginning in the 1990s, but they in fact account for the combinatorial structure of the space. And it is possible, now one would ask, why would you want wavelets on this structure if there are no signals that you can analyze with them? That is not exactly true. There is a standard way of taking wavelets, functions on this group, and putting them, let's say, on the 0-1 segment, and then you have functions on the real segment, and you can start using them. Applications, as I said, have not been developed, but perhaps this can be further looked at. And I tried a little, but not too hard. So for the moment, this is limited to extending these abelian association schemes to infinite orders, which we did with Maxime 2 or 3 years ago. For the moment, we stopped there. But orthogonal polynomials are replaced by some type of wavelets. So then, to conclude, there is a list of references that were useful for me in the course of this work. As I said, it developed over the years, and it was by no means a full-time occupation. There were other things, such as polycodes, such as codes for locality, the distributed storage applications. There were other works. But here is a set of papers or books that influenced me to a large extent in this work. And this talk is based on joint works, as I said, with a number of colleagues. The students' names, again, are underlined, and it extends even to this ISIT, to a paper by Talha Gulcha and Minier, presented on Monday. And that goes about the construction of non-binary polycodes, where that multi-level polarization, again, played a role. There are also some other works that I mentioned in the abstract, but not here. There was a work with Andrew McGregor on error exponents for the binary symmetric channel, the Gaussian channel, which again developed from this approach to the analysis of codes, and that brings me to my conclusion. Thanks for your attention.
Okay, thank you very much for a beautiful overview talk of metric codes. Are there questions for our speaker? I have a question concerning your polarizations.
Yes.
So is there similar things happen when you have similar things you have when you have a multiple access channel or broadcast channel?
Yes.
You have also different polarizations going on. I was wondering, is there a connection between these?
Definitely so, and this was highlighted in the work by Manuel Abbe and Emre Telatar, where they did their polarization for multiple access channels. What is slightly different is that classifying extremal configurations for max is more difficult than in this case of non-binary alphabets. At least that's my understanding. Here we have an explicit description, even though, as I said, given a channel, so you give me a channel, I cannot tell you if there will be 2 levels or more than 2 levels. This question so far is unanswered.
Any questions from the audience? If not, let's thank the speaker again.